Video, we describe a method for efficiently rendering high-quality images of low-resolution geometry using silhouette mapping. The silhouette map is a data structure that stores in contour form the silhouette of an object as seen from a number of views. The views are represented in this visualization by the vertices of a star-shaped polytope. We use these samples to interpolate silhouettes for arbitrary views to which we clip the low-resolution geometry. On the left, we show a 3-hole torus modeled with 11,000 polygons. On the right, we show a low-resolution approximation that has only 500 polygons. It has been shown by many people that one can create a convincing appearance using low-resolution geometry along with high-resolution textures. We start with the same approach. We use 20 pre-rendered shaded images of the high-resolution geometry as projective textures applied to the low resolution. The one feature that such an approximation cannot reproduce are high-resolution silhouettes. In our system, for each current view, we find 3 nearby silhouettes in the pre-computed silhouette map and create an interpolated silhouette. The low-resolution geometry is then clipped to this silhouette. We do so by rendering the contour into a stencil buffer. We can also use the contours to directly set the alpha values, giving us an anti-alias silhouette, which in fact looks better than the original data. Next, we describe the silhouette interpolation process. For each current view, we find the 3 nearby views shown in red. On this triangle, we find the closest edge. The 2 associated silhouettes are shown in red and green on the upper left. They are rectified using the epipolar constraint. An intermediate silhouette is interpolated, shown in yellow. This is done with an algorithm described in the paper. The silhouette interpolation can interpolate between contours with different topologies and is guaranteed to be a conservative estimate of the actual silhouette. In the second stage, the intermediate silhouette is rectified with the third view to create the output silhouette. The output silhouette is unrectified so that it matches with the current view, and now silhouette clipping can be performed. Since the current view is typically not on the polytope, we apply a projective transform to the resulting contour before using it for clipping. This step is just an approximation to the true silhouette evolution. For example, if we move away from the object, we will simply scale down the silhouette contour. In order to create the silhouette map, we begin with a large number of silhouettes seen from a large number of views, in this case 1024. A simplification algorithm described in the paper is run progressively discarding views that can be predicted well with remaining data. Here is one with 500 views. Here we see a silhouette map with 128 views. In regions where the silhouette is easy to predict, large triangles are produced. In regions where the silhouette is hard to predict, such as where its topology changes, smaller triangles remain. In this example, we see that views are kept around to represent the topological changes that occur when the number of apparent holes changes. In some regions, the topology is simple, but due to low surface curvature, the silhouette can slide clear across the object as we move a small amount. Once again, small triangles must be kept for that region. Here we show a high-resolution bunny model with about 60,000 polygons. On the right is a low-resolution progressive hole model with only 500 polygons. Once again, we use 20 pre-rendered textures as projective textures to apply on the low resolution. Note, though, that the silhouettes still look quite coarse. we can produce dramatic improvements for this model using our silhouette clipping algorithm. Texturing is the slowest part of this rendering pipeline. With it turned off, we can interpolate high-resolution silhouettes in real time on an SGI Indigo impact. In this video and paper, we describe a data structure, the silhouette map, that represents the silhouette as seen from a number of views. We describe an interpolation algorithm for producing silhouette contours for an arbitrary view at runtime. This is used with silhouette clipping to efficiently produce high-quality images using very simple geometric models. Once again, finally, in this case is the bunny with only 500 polygons.